maybe I can answer some of them in this talk. This talk is a little more theoretical than the Monte Carlo one, but I will try to give you again the flavor of the methods rather than the details. So what I want to emphasize in optimization techniques is that this is a very complicated and interesting area. And there's a book that is really interesting more from a theoretical perspective than from a practical utility. But it's Norman Acton's book, and he calls it Numerical Methods That, and in very small type, there's usually work. This is actually a 1970 book that was reprinted in 1990. And the reason is that optimization methods and many other methods that numerical analysts can pull out of a hat are very complicated. And just like all these interesting discussions we've had on Monte Carlo, on molecular dynamics, there are cases when they fail, even the best methods fail. And therefore, it's really important for an application person, like I would say half of you at least are interested in biomolecular applications, to understand the background and the theory behind the methods you're using. Now, in particular, Foreman Acton, who wrote this book about laughing about these numerical methods, he hated the most, or he mocked optimization methods the most. And I'll just read parts of it. And he opens his chapter on optimization by saying, "It was a sense of reluctance that your author introduces this topic, for minimum-seeking methods are often used when a modicum of thought would disclose more appropriate techniques. They are the first refuge of the computational scoundrel, and one feels at times that the world would be a better place if they were quietly abandoned. But even if these techniques are frequently misused, it is equally true that there are problems for which no alternative solution method is known, and so we shall discuss them. A better title for this chapter might be How to Find Minima If You Must." Okay, well, we must in many applications of molecular simulations, and it's actually not as difficult, and certainly there has been tremendous work in the last, certainly since 1970, since Acton wrote this book, and there are now pretty good techniques, but we still haven't solved the global optimization problem, and local methods are limited for what they are, even the best of them. So in this hour, I want to cover a selected topics from this list. I want to, in order to whet your appetite about the importance of optimization, I want to mention some commercial optimization techniques, and so you become familiar with some of the possible difficulties. And this is from a recent conference in Minneapolis that was on optimization technique and how they affect commerce and everyday. Then I'll go to very rudimentary issues and how you define an optimization problem, and the fundamental method, the Newton-Raphson-Simpson-Fourier method, and everyone calls it Newton's or Newton-Raphson for short, but it really should be equal credit for all these, and I have a historical perspective of why when I started to do research on that. It really is unfair to credit Newton or Newton-Raphson all the credit for this method, because it was really a team effort by all these researchers. And this, for short, I'll call it Newton's method. This method is the fundamental basis for all the other methods that are used in optimization that I'll describe later. Some of the theoretical aspect I'll just mention, that what convergence order and ratio, how you judge a quality of performance of an optimization method, how how you apply it to minimization. Newton's method was originally developed for solving nonlinear equations, and then it was extended for minimization. And then I'll discuss the typical methods for biomolecular that are used, and you're probably familiar with conjugate gradient, steepest descent, and the Newton-type methods, which are quasi-Newtons, and truncated Newton, which are really the state-of-the-art type methods. So first, to emphasize how important optimization is, bless you. There is, in everyday life, optimization is very is important, and I'll give you two everyday examples where commercial examples where optimization experts have made a lot of money actually at solving these hard problems. So this is from a conference that was convened at the Institute of Mathematics and its Application at the University of Minnesota recently, a year ago or so, and brought together all these experts in optimization and commercial optimization from different areas. And it was really interesting to hear about their different experiences in with actual optimization problems that exist out there in the world. And I'm only mentioning this because you'll maybe appreciate that these problems are so hard, it makes our problems in biomolecular systems seem impossible, because these problems are much more well-defined than our chaotic systems and so on. So some of the examples where optimization routines are very important is in aircraft and aircrew scheduling, truck routing, mass transit system, and just New York City alone has 5,000 buses and 300 routes every day. And they have to change the rules when President Bush comes to the city, or some other dignitary, or there's some parade somewhere. So this is a very difficult kind of networking problem. And online grocery system, I'll also describe the problem there. And in fact, there were examples in this conference that many of these companies do not have people who are really experts in optimization. And when they when they hire them, they can actually save a lot of money. And that was the case of Air New Zealand, which is a problem I'll show you here. That $8 million was saved by good optimization routines for their aircrew scheduling, and also for the grocery delivery service. So let me just describe what aircrew scheduling. Essentially, the problem here is for an airline needs to decide who flies, that is, the pilots, the crew, which planes and where. So they have all these routes they must cover. They have all these pilots. They must put them to work. And these pilots have, and all the other personnel, they all have rules of how many hours they can be on the air, how many hours they need to be on the ground between flights, how many vacation days per week, per month, how many rest days per month, and so on. These are all considerations. So essentially the way it's done is the first step is you have tours of duty, what's called, you schedule the air crew, and the idea is to minimize the crew-related cost, for example, the overnight stays of all the crews, while covering all scheduled flights. So that's the first step, and then that's who's flying. And the second step is the line of work. Now you need to schedule for all these crews. There's vacation, training, flight duty, and so on to maximize the crew's satisfaction. For example, you want to give them a week of vacation per month. You don't want them to have a day off after every day of flying, because they can't do much with that, while covering all tours of duty. So it turns out to solve this kind of problem, that's an NP-complete optimization. It's a very hard non-polynomial type problem. But matrices and vectors have special properties that can be exploited for linear integer programming methods where the solutions are known. But this is what interested me, to understand the interaction between the economics of this process and optimization, is that it turns out that the reasons that not having resident experts on optimization can cause problems to airlines, because airlines are very greedy. So they look at minimizing the overall cost, and of course they want to maximize the worker and customer satisfaction, but their solutions turned out to be non-robust. In other words, the solutions that lead to the minimum cost are very prone to catastrophic problems. So if one pilot is sick and that pilot was scheduled to fly 6 days in a row, then you have a huge problem. And if you have you schedule flights that are too near in time, then if one is delayed, you have a domino effect and they're all delayed. So it turns out for Air New Zealand that this expert optimization person that they hired was able to build in robustness into the solution by these elastic constraint of possible disasters that will happen, thunderstorms, sickness, whatever, and by allowing some higher cost at the expense of having more robust solutions that is less prone to these disasters, you can actually do a lot better in these optimizations. So I think as I'm saying this, I think about molecules and think about a certain bond that you can make a hydrogen bond be very perfect, but that will disrupt another region of the molecule. So also in molecular structure, you'll have optimization orchestration going on over the entire system that builds in kind of robustness for a molecule to perform in the cell. I'll just mention quickly another interesting example on online grocery that is again a optimization issue, and you may have heard of this company called Webvan that went bankrupt in 2001 because they didn't know how to schedule their deliveries. Online grocery system is a very complicated business, actually, because they have to compete with the customer has options. So you can afford to wait for you have no choice but waiting for the plumber to come in 2 days, but you can simply go to the supermarket and buy your milk and bread and ice cream. So you're only going to order groceries online if you can get quality products quickly and conveniently. So it's challenging because the optimization there is that you have many customers, you have large orders, and the customers need to be home to put their milk and ice cream in the fridge and freezer. So they have to give windows of time when delivery can be made. So it's a very complex scheduling. And Webvan went bankrupt because they just accepted all the customers, essentially, and they gave free delivery. So they really had an awful system. And it turns out, in order to deal these problems efficiently using optimization, you have to accept when an order comes in, you have to decide whether you accept or reject a grocery order. And you only accept it if you can build it in the network, a delivery route, and within the window acceptable. And if you can't, you allow the customer incentive so that, if you can't get the groceries by 2, but you can get them by 5, you'll give them a 20% discount. So this is a very complicated business, and again, these techniques, they're these commercial examples that when they've hired optimization experts, they could have increased their their income by a large percentage. So, okay, so I deviated a little to illustrate how complicated optimization is, and certainly we have that in molecular systems. So now to more basic things, how we define optimization problems. These are basic categories. They can be constrained or unconstrained. Simply constrained means you have a certain region of phase space. So in this one-dimensional example, this is x. This is the function that you're trying to minimize. Say in many problems in mathematical biology, x must be a non-negative integer because you're talking about a real physical quantity. And so on. In molecular systems, you may have, you want to constrain this certain region, this region of the molecule to be fixed or so on. And minima that you all know, the global minimum, local minimum, and you have weak local minimum in the sense where you have a plateau, so it's less than or equal to, rather than locally a minimum. And depending on the formulation of the problem, you have different methods that are appropriate for them. Now, we've talked about Monte Carlo methods, and that's kind of what you have in simulated annealing type of problems. So if this was your function, you can wiggle, you could start here, and theoretically you can get out of a local well and move and find the global minimum. Whereas local methods like Newton's method and the variants that I'll describe are greedy descent methods. So they're only guaranteed to find the lowest a minimum. So they can tell you nothing about the global minimum. You may happen to find it, but convergence of a local optimization methods means that you just have a minimum. And there are many interesting methods that try to combine them. Sharaga pioneered in the late 80s this tunneling method, which is a very nice and has this intuitive appeal that you use a greedy descent method to find the lowest basin, and then you do some kind of tunneling, through past the tunnel, and do a combination again. So there are methods like that, and it's quite difficult how to extend it to larger systems. But it's a very clever idea. The basic structure of a local minimizer is the following. So you start from a given point in configuration space. You calculate a search direction, PK. Now, all the pictures here are just one-dimensional, of course. But we're talking about many, many variables. So the way to extend these things is instead of scalars to work with vectors. But I'm just trying to introduce you the concept. So in a vector format, then X would be a vector, P would be a vector, and so on. And a typical and molecular application, X would be the Cartesian coordinates of all the atoms. Defines a structure, or it could be internal variables that you're working with. So the basic idea is that you start from some point, xk, calculate a search direction, that's pk, and these are pretty, the names of these are standard in the optimization literature. And then what you do is determine an appropriate step length, lambda k, that you'll march. So you have xk is a point in configuration space, p is some search vector, and the idea is that you minimize the function along that direction. And that defines the next point. That defines lambda, the step length, and that defines the next point is just lambda times p. And lambda is typically a scalar between 0 and 1. So the heart of, and then you have a new point, xk plus 1, and then you continue this process. So the heart of the method is how to calculate the search vector, how to calculate the search vector pk. in steepest descent, pk is minus the gradient, and the gradient is the vector of first derivatives. And in other methods, pk is more complicated. It tries to build up information as the algorithm proceeds. And of course, this is a very schematic structure, but the idea is that if you use a suitable method that converges in locally, then you can converge to a local minimum. And here is the definition we all need when we're talking about multivariate function. The gradient vector is simply the vector of first derivative, so delta fx, and these are component y, and it's an optimal point where the gradient is 0. That's just a extension of the first derivative being 0 at a critical point. And the Hessian matrix, which is the matrix of second derivatives, is at a minimum point. An optimality condition is that this is positive definite. And that's a generalization of positive curvature. Often to describe progress or in the optimization literature, it's important to become familiar with contours, two-dimensional contour curves or quadratic function. And this is just to illustrate what this positive definite notion means. So if your objective function was this quadratic function, this is x, that's a vector, and b is a vector, and a is a matrix. So you could see that when a is positive definite, this is, I showed here the values because you essentially have a bowl pointing up, so you indeed have a minimum. When it's negative definite, you have a bowl pointing down, so you have a maximum. When the matrix is indefinite, you have this case of a saddle point or singular when it has a 0 value. So these contours are useful for reference. And of course, in 3D, what those curves essentially show is that's the positive definite case, the negative definite case where you have a maximum, a minimum, indefinite where you have a saddle, and a singular where you have a plateau of this kind. And these kind of singularity can be particularly problematic for optimization. So as I said, the Newton-Raphson-Simpson Fourier method was a classic technique, iterative numerical algorithm for solving a system, nonlinear system, f of x equals 0. And of course, it was started before Newton translated it into calculus, but it was developed before calculus was formulated. So it's only now that we've replaced the actual formula with that Newton was able to replace it with these derivatives. So it was developed for solving a nonlinear system, and then by simple extension to minimizing a function. And essentially, it's by iterative that, just like you saw, that you generate x0, x1, x2, and so on in an explicit function in such a way that the limit of the function value is 0. So you're solving this system. So this is the method. The method is very simple, that you have an iterate xk, and xk plus 1 is defined as xk minus the f over f prime at that xk. So of course, this is only defined as long as the derivative is non-zero. So the basic, how is this obtained? Well, this is just a simple idea of how. If you write a function, remember you're trying to solve f of x equals 0. So if you expand this in a Taylor series, knowing the derivatives, and you want to minimize f of xk plus 1, and let's say you quit after the first derivative, the condition that this is 0 gives you this, this formula. And Newton was the one, actually, in 1665, he used it to solve a polynomial, to find the roots of a polynomial equation, and that's what he derived. And the precursor, this was before calculus, that actually replace this derivative by a finite difference in a secant method. And they're closely related to quasi-Newton methods today. Now, Newton's method has a very simple geometric interpretation that's easy to understand. So this is the function. You're trying to solve for the roots of this function. In other words, you're trying to solve this x where f of x is 0. So if this is your x0, this is your this is the slope at x0, and you take the next point as the intercept of that slope with the x-axis. Then you have this is the slope at x1, and you take the intercept and so on. So in a sense, this slope is the search direction that's later used in more sophisticated methods. So this is the ideal case where everything behaves well, and the derivative of this function, as you can see, that's where the tangent is 0. You're not in that region, and everything works fine. But when you have the tangent close to 0, you could see that the slope can take you way out of course. And it will, and it could take you a very long time to get there. So if you imagine if you're this, then your solution would be over there. That's where you hit the x-axis. And then whatever the function value there, you'd have to take the slope. And eventually you can wind back, but sometimes you just leave the domain and go and never get a solution. So these would be poor starting points. And again, you have further difficulties when this is a root, but it's also a minimum. So you have f of x and f of x prime are 0 at the solution. So you have particular special problems, and here you have an inflection point. It's not a minimum, but it's an inflection point. And again, you could see that if you were to take the slope over here, you'd again go to a far off region there. So you should keep this simple picture in mind, because in practice, all these cases do happen, and it's not hard, because especially when you're working with large systems, so you need to have caveats to detect when your solution is going way off track. A classic application of Newton's method is to just calculate the square root of a. So if you ever need to calculate the square root of a and you have no calculator, or you could always use Newton's method and get a very accurate answer. So if you're trying to solve x squared minus a equals 0, this is Newton's method. Xk plus 1 is the average of xk and a over xk. So the computer implementation here is just what you could see. This is, you could start if a equals 9, so the solution is 3, and we start pretty far away. We start at 6. Then you could see this is the error and the iterate, that very quickly Newton's method converges. And in fact, if you look, let's just look at the double precision. It's hard to see, but all you need to do is really look at the error here and see how the error decreases by an order of, by double order magnitude. So if the order is 10 to the minus 1, here it's 10 to the minus 2. And that's the beauty of Newton's method. You get a very quick convergence. Of course, this, after that, that's machine precision. So after that value, it's meaningless. But I mean, the further improvements are not important. But that's why Newton's method is so appealing, because it's quadratic convergence. So it converges very rapidly, and essentially in practice, what means that if you have t correct digits at step k, you have 2t minus 1 correct digit at the next step. And of course, that's beyond a certain value. So at the beginning, you may have until you reach the region, and you can experiment with this with points that are very far away, and you'll still get very good behavior in general. So I mentioned this quadratic convergence. How do we precisely define it? If you have a sequence, xk, that converges to this x star, that's the solution, you let the error at each step be xk minus x star. This is, of course, a theory, so you know the solution. Then you define, how do you define convergence ratio and convergence order? You say that the sequence converges to x star with order p if p is the largest number such that the limit beta is finite, and where ek plus 1, the absolute value of that, divided by ek to the pth power, the limit in that is that finite value beta. And here are just some examples. So if you have a sequence of, this is a sequence of numbers, and you could just apply this formula and find that when you put p equals 2, you get a finite ratio. This means it's a quadratic because p equals 2. This sequence, when you just apply that formula, you get a ratio of beta is greater than 0 in this case. It's 1 here. You get this ratio. That's linear convergence. And p is also 1 here, but beta is 0, so the limit is 0. That's called superlinear. So quadratic is better than superlinear, and superlinear is better than linear. And these are important in defining the optimization methods that are available. And of course, this is all in theory. In practice, there are many other considerations that affect the problem: accuracy, conditioning, and so on. So I just want to give you an idea of how the proof is sketched for this quadratic convergence of Newton's method. It's actually quite easy. So all you need to do is to compute that formula, relate ek, the error at step k, to the error at step k plus 1. So it's all done by expanding in this Taylor series and obtaining in closed form this relationship that defines the two errors. And you could see that's where the 2 comes in. And you get this ratio beta. And with these assumption that the root is simple, that is, that you don't have a gradient, that the derivative is not 0 nearby. And in practice, you have convergence only for a simple root and only when x0 is sufficiently close to the solution. And the convergence for a simple root, again, is done by mathematical induction. That's how you prove this. And this can be done for other methods as well that are applied in practice. Now, in practice, you have to implement safeguards. So if you have a Newton, in the case of Newton, you have a Newton search direction, that's the slope. So the slope may take you very far off. So sometimes you want to dampen that search. So you want to constrain, say, pk to be in a certain regions in order for you not to go off in a terrible region. So that's important in practice. That's called bracketing strategies. And also, it's important to halt the minimizer when no further progress is being realized. So you often have the convergence criteria, especially for novices. You may ask the convergence criteria to be too strict so that the gradient is very small, for example. And the program will just go on and not make any progress because it will never reach there. Maybe it can't. So it's important to have a limit on the number of iteration. And how do you assess progress? You compare consecutive values when they become very close to each other. You can, that's consecutive variables, the x's. You can compare consecutive function values and all these things. So in practical implementation, there are important restrictions, and also they depend on the machine precision, and that's why often optimization routines require double precision. Okay, now to the application of Newton's method to minimization. That's a pretty straightforward extension. Again, the method as was derived was for solving a nonlinear system. To minimize a function, the idea is very simple. So here again, you have a quadratic rather than a linear model in the expansion. So again, if this is your function value, now you're trying to minimize that function, not to solve it for 0. So you have this quadratic model, and when you minimize this value, because this is a constant, you have to minimize this, and minimizing this leads to this iteration process. So now, in order to apply this method for optimization, you simply replace f divided by f prime divided by f double prime in this. And this is for a one linear example. And in vector form, you have a gradient that replaces this first derivative and the Hessian matrix that replaces this. So this is a Hessian vector product over here. But you need the inverse of the matrix. So that's the inverse of this. So in vector form for a nonlinear function, you get, for a multivariate function, Newton's minimization iteration is the following. The next step, xk plus 1, is the old step minus this product. This is a vector. This is the inverse of the Hessian times the gradient vector. So now, of course, we're getting into this more complicated expression where for Newton's method for minimization, you need the Hessian, so you need the matrix of second derivatives. If you're working with a large system, this is a huge matrix. And moreover, you need to inverse. You need the matrix inverse. So you need to actually get this product. So P, remember the basic structure of an optimization method. So you are P, that's the search vector by which you scan at every step, is defined as this product of minus H inverse G. And another way to write this is that H times P equals minus G. So you don't need to invert a matrix per se, but you need to solve a linear system at every step. So H is fixed. So in practice, that's what Newton's method means for minimizing functions, that in order to solve for the search vector, you have to solve a linear system at every step. Now in molecular applications, the Hessian is sometimes has a structure. So when you're using, now people use, don't employ cutoffs for non-bonded. But if you were to use cutoffs for the van der Waals in electrostatic terms, or if you were to approximate the Hessian just by those local terms, you will have a structured matrix. So in other words, you will have many zeros in your matrix. And here are Hessian patterns. So this is a matrix. These are the dimensions, the variables of the system. And these are cutoffs, say, implemented at 8 angstroms. And this is for a small system, alanine dimer, a butane, and a protein here. And this is without solvent. So just if you get an idea, you have a very ordered structure, and here are the solvated systems. So you have much bigger over here. So you have patterns emerging. Each block has a pattern, and that's because you have, from the local terms, you have a range. So bonds have a range of so many atoms around them. Bond angles have another radius of interaction, and so on. So it turns out that these structured matrices of the local interactions are very important for developing tailored optimization methods. And here are some examples. As your system size grows, and these are for larger systems, you can see more variables. Then you have all these patterns, and you can exploit them in the methods. Okay, so now to more practical issues of implementing these Newton methods for minimization. Their strength, and I will mention, yes?
You give us opportunity for 5 minutes questions.
Yes. Do you want now? How much do I have?
So we still have altogether 10 minutes.
Okay.
We have the general question period. So if you would finish in 5 minutes, then you would have still have 5 minutes or even more for questions.
Okay. So I will try to summarize these in 5 minutes. So the idea is that Newton methods are based on second derivative information, and that's why they can be they take more work, but they are also, you get the benefits in the convergence. So if you're using standard packages, the second derivatives have already been computed for you. And there are many variants of Newton's method that balance the amount of work and the computational requirements with the practical performance. But the idea stems from computing the search vector, and in some cases obtaining, if you don't have the complete Hessian per se, you have some approximation. And the two competing methods, there were some questions during the break of which methods, optimization methods, do I recommend, and for which problems. Well, these are the state-of-the-art methods in the optimization community for multivariate functions, and they're limited memory quasi-Newton methods and truncated Newton methods. And both of these balance the requirements, the computational requirements with convergence, and they really make methods steepest descent or conjugate gradient quite obsolete. So the idea in limited memory BFGS method is that you don't want to require the user to have the Hessian per se, but you build up the curvature as the algorithm proceeds from the gradients. And in truncated Newton methods, you actually solve the system, the linear system, the Newton system, iteratively, so that you truncate the process as long as you have a search direction, because you don't need to solve it accurately. And truncated Newton methods require partial second derivative information. But they can be very effective in the case of molecular structure, where you have a structure to your Hessian. I just want to emphasize all these methods use line searches. So that's the damping. Once you have the Newton search vector, the search direction, you need to do a one-dimensional minimization along that direction. So you scale that search direction, and that's important in practice. Now, the competing methods, as I mentioned, are nonlinear conjugate gradient and steepest descent, which you probably are all familiar with. These do not require any second derivative information, and steepest descent is very simple. Excuse me. steepest descent essentially sets the search vector at each step to be minus the gradient. So you're going in the greediest direction of function reduction, and it's often it's gotten this reputation for being very good at the beginning for quickly reducing the function value from poor starting structures. But if you have a conjugate gradient or a Newton method, it will do that. It will automatically use even better search direction at the first step. So there's really no need to switch method and use steepest descent and conjugate gradients. It's still today people use it, this kind of protocol, but it's totally unnecessary. The problem with steepest descent is that even if it performs well at the beginning, then it can just get stuck and never converge later on. Nonlinear conjugate gradient is a very simple method as well, and it's the recent in the recent literature and optimization. There were all these interesting relations between nonlinear conjugate gradient and quasi-Newton methods, which explains its reasonable performance in practice. So it's very cheap, it's very modest in storage, but often but it can work great, and then sometimes can work not so great. So typically Newton-type methods give you are more robust and reliable performance. So just to illustrate, and I'm going to end by showing how these methods perform on simple and realistic molecular problems. This is a function, an artificial function that's constructed. It's called the Rosenbrock function. You can use as many dimensions as you want in it. And it's a tough problem for optimization because it has a banana-shaped valley. So the minimum is hidden here at 1, 1 over here. And so it's a very narrow valley that must be found. And this is, again, the two-dimensional contour. And what I'm showing here, this is nice so you could see the progress. This is steepest descent. And if you start over here, then, we'll take the steepest descent and then make this progress. But here, after thousands of iteration, it will converge to the solution very slowly. A conjugate gradient type method performs pretty good on this problem. In this case, it happened to do very well. But Newton methods are much more direct in their progress. You could see that they go very systematically along function curvature, and this is a quasi-Newton type method, and truncated Newton method, they go very systematically along the valley, and that's the ideal progress that you would like. Let me show you another examples of these different paths. This is for a more complicated function of two variables. These are the function contours. They're all the same contours, but we're showing them here at different darkness. This is the minimum over here. Again, it's a very narrow ridge. And so steepest descent started here, takes you back, and never really gets there. Conjugate gradient happened to work just great in 3 steps, and the Newton methods work very well in this case. And of course, the CPU times are proportionate to this progress. And finally, this is for realistic molecular applications. These methods are compared, and what is shown here is, as a function of iteration number, you are seeing the, this is hard to see, but this is the gradient norm. So you want the gradient norm is what you're trying to force to go 0 or 10 to the minus. You have a convergence criteria. So typically, ABNR is a Newton type method that's in Charm. This is conjugate gradient, and this is a truncated Newton method that our group has developed, and it's freely available on our website. And so you could see in general that ABNR conjugate gradient take quite many iterations and can take detours toward the solution. And Newton-type methods, also quasi-Newton type methods, work quite well. So at the end of the chapter that I've also given you as handouts, I believe you have the PDF files, you'll see a whole bunch of recommendations for minimization. And often you want to use, someone asked me at the break also about, you use one method, you find this minima, you use another, you find lower minima. And of course, you can't answer very simply, this method is better. Rather, you have to try many different starting points. You should experiment with more than one optimization method if you can. And you should always keep in mind that these methods are local in nature, and that there could be artifacts, again, like in the random number generator case, that are associated with your function. So, for example, in the early days, this was actually very interesting. The early models of DNA where the phosphates were not properly screened, if you were to minimize those kind of structure, the DNA without the proper backbone electrostatics, the DNA strands would unwind. So you would not get a helix structure. If you were to use cutoffs and minimize a protein structure, you're going to have artificial minima at the cutoff value. So if you have cutoffs at n angstroms, you will have artificial minima at that corresponding to lower values, of course, when you have the electrostatics is 0 at that point. So it's also very important to understand some background of the optimization method and to question the answers that you get for possible artifacts that are stemming from the potential energy model itself. Okay, thank you very much, and I'll be glad to answer more questions on optimization.
Okay, let's give Tamar. So, I'm very sorry that we have to go to our general question period 2. So we will definitely have a few questions because that would be just not right in the spirit of the school. But I just ask you that maybe we're just making it in a few minutes, and the question should be concise, the answer should be concise, so that we may be able to address a few questions for the first and second.
What if you don't have an analytic form for your function?
There are methods for for those kind of functions, and that are, but they're much more complicated, obviously. There is a whole class of methods. If you don't have an analytic, you could have a non-continuous function. The derivatives don't exist. So
I just mean where you have to evaluate functions.
Right, by x and yeah. Again, it's hard to know if you don't have any properties of the function, if you don't have continuity or those things. So all these methods, I want to emphasize, assume that you have a function, you have basic continuity. That's very different methods are applied for these special cases.
Okay, yes?
You've shown several graphs for sparse patterns you produced from molecular simulations. And the question is, how you produce those? Did you use analytical forms of those Hessians, or you use automatic differentiation tools?
No, these are just from evaluating. You have a potential function, you evaluate all the interactions, all the bonded interactions in that case, and then then you look at each derivative, each entry of the Hessian. If it's non-zero, then it's an entry in the Hessian. If it's 0, then it's 0 and it is blank.
Right, but for the interpretation,
How do we evaluate them in practice? Yeah, this is analytic. Yeah, these are the codes, yes. Automatic differentiation is tricky, is very tricky, or if you need use analytic derivatives because you have the finite difference, it's very tricky, and it requires 2 gradient evaluation for every column. So in the case of molecular application, there's no excuse for using that because we have forms. They're messy, but people have done it. It's available. So you might as well use the analytic forms. Okay. Any other quick question on optimization? Yes?
What about neural networks optimization? Is it
Ye-
possible?
Yeah, these fall into, there are many type methods like that, and I would say they might fall in the border with Monte Carlo and other stochastic methods. Okay.
Okay, thank you very much, Tamar. So we have now a few general comments, and then possibly questions from you. So I just would like to go over the program this afternoon quickly. We have after this general question period, we have the feedback forms that will be handed out, and we would like you to fill them out and return them to us. We will have 2 types of feedback forms. There's some echo here. Maybe I'll go a little bit over here. Okay, that would be nice. The feedback, today we have more the general feedback forms on the sort of general characteristics of this school. And tomorrow, when we are done with all the lectures, we will give you another feedback form for the individual days, like for the day on molecular graphics, on steered molecular dynamics, and so on, so that we are knowing better how you felt, how relevant the material, the specific material is for you. So this feedback form is more on the style of the conference, and tomorrow's feedback form will be more on the content of the conference. So then we have the hands-on this afternoon for an hour on the numerical methods. There is some material for you that was already handed out earlier. Those who didn't get it might want to pick it up